Instead of just talking about finding crystals, I'm going to expand it a little bit and just talk about the outcome of the crystallization experiment. So it could be anywhere from clear drops to crystals to skin to other outcomes that we could see. Again, this is mostly going to focus on soluble proteins. So you already know this. What's a biomolecule? What is a crystal? So you've got a periodic array, a three-dimensional array of these macromolecules that have a lot of water associated with them. And the waters, you can think of the protein molecules like islands separated by water with these very weak bonds holding them together. Right? You've got these beautiful solvent channels that we can use to flow small molecules into the protein to actually bind to the protein while it's in a crystal lattice. This is all disordered water. And then we have this hydration sphere of ordered water around the protein molecules. And it's just a cryo-EM image from McPherson's work that actually shows the black are the water channels, and you can see the white protein, the beautiful symmetry that the crystals have. If you have crystals like this, it's very easy to tell that they're crystals, right? They're big, they're visible, they're easy to spot. But if you look at something like this, maybe the first experiment up in the corner you could look at and say, well, yeah, there's a crystal there. But the rest of them, you'd be hard-pressed to sort of spot crystals just using visible imaging, right? They don't look like crystals, they look like precipitate to me. But if we use something like the sonic second-order nonlinear imaging of chiral crystals, you get a second harmonic generation that actually tells you that you have chiral crystals forming in these drops. So if we just rely on visible imaging, we can miss a lot of outcomes that are actually crystalline that are forming in our experiments. So again, imaging technology is critical for crystallization screening because if you set up a plate, I don't care how many experiments you set up, if your vision, if your eyes aren't good enough to see the crystals that are forming and you can't detect it by any other means, then you've missed the hit and your experiments has to keep continuing to try to find some initial conditions. So most people use some kind of an imaging technology that's based on standard microscopy. You either go to a microscope and look through it, which is very slow but gives great high-resolution data on what the outcome of the experiment is. But it requires some kind of visible crystals, right? You can use automated imaging systems, again, capture images, but still they're relying on standard microscopy to detect the crystals. Right? If you don't have visible crystals, then you don't have any place to go except back to formulating the protein and trying to set up more experiments. Right? So crystals, when they're forming in the presence of a skin or a precipitate, which they often do, they're very difficult to see. This is the second harmonic generation sonic image that actually shows that there are crystals in this image if you can't see them from the back of the room. But they're difficult to spot, not because they're small, but because they're just sort of hidden behind opaque precipitates. And the same thing here, where you've got a skin formation. The sonic image shows that there actually are crystals in there, and you can see them near the front of the room, near the back of the room, I'm not so sure. So it's not just a matter of the size of the crystals that you're trying to identify, but if there are other objects that can distort or make it difficult to verify and confirm that you actually have crystals in your drop. Now, I'm not going to go into the physics behind this, but one of the methods that you can use to detect crystals, two methods that you can use, are second harmonic generation, which relies on a frequency doubling effect. It's a nonlinear optical effect. And it will be able to detect chiral crystals if they're present. And if they're of, basically, it will fail to detect high symmetry crystals, but will detect lower symmetry crystals and chiral crystals. And the other thing that you can use is a technique called UV2 photon excited fluorescence. And that won't tell you anything about the crystallinity of the sample, but it can tell you if the sample that you're looking at, the object that you're looking at, contains protein. Which is a valuable thing to know, even for detecting and validating whether you have a protein liquid phase forming. But if you have the combination of the second harmonic generation and the UV2 photon excited fluorescence, then you have concrete verification that first you have crystals from the SHG, and second that you have protein crystals from the UV. Okay? So we can integrate the sonic with standard imaging. The sonic it's great, it has a lot of huge benefits. It relies on a femtosecond pulse laser. The femtosecond pulse laser, every once in a while, goes out of commission, so every several months has to be replaced. The sonic is expensive. It's a $500,000 instrument. When it goes down, we don't have a backup in place. Most people don't have a backup in place. So if you're solely relying on the sonic, and you don't have any other means available to identify crystals, microcrystals, to verify them, then you're leaving yourself open to having some issues. The other thing about the sonic is that it takes quite a while to actually take images. So it's a confocal technique. So the laser is actually being focused and oscillating on different planes. So you're taking slices through your drop, and then software will combine those slices into a single extended focus image. It takes a fair bit of time to image a plate. So the sonic can image about 32 96-well plates, giving the full visible SHG and UV imaging of the plate in 24 hours. It can only image, we've got it now so that it can image about 4 of the 15 36-well plates in 24 hours. So we don't have enough sonic time to be able to just rely on that and not anything else for imaging. A nice thing about the sonic is you get black background for the SHG and white for signals. So if you have crystals, it's very fast. You can look at a big set of images at once, and you can sort of tell, okay, there's white here, 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 here. You know you've got chiral crystals showing up. So it's a very rapid way to look at a lot of data at once and figure out if you have crystals forming. So that's one really big benefit of it. It's a very high throughput technique. Typically, the UV and SHG are great for identifying protein crystals, but we can get false positives with some salts that form chiral crystals. Unfortunately, some of these salts are very good for crystallizing proteins, so you can get false positive SHG signals. And the UV to photon excited fluorescence, again, you can get some false positives from certain salts. So it's not a foolproof method. There are exceptions, just like everything else in crystallization, but it's a very good tool to have at your disposal. Okay? So again, seeing crystals directly relates to structural output. If you don't see crystals, like in this bright field image, you don't see crystals, you don't go on to optimize to get a structure to collect data, do anything else. So this is that same image that we saw in the previous slide. So when you look at this, you really didn't see much. But when you look at the SHG and the UV, you can tell that you have chiral crystals present, and you can tell that you have protein chiral crystals present from that combination. And that means you can move forward with your experiments to actually get the structure. So, and just a few more examples. These are the original crystals, and these are the optimized crystals. So this isn't an outcome that typically we would have tried to optimize, but sonic showed that it actually was crystalline, and we could optimize to produce large crystals. So I'll talk a little bit now about what other kinds of outcomes you can have in your experiment drop and how you can look at it, assuming that you don't have a sonic that's readily available to look at your experiment plate, which most people don't have. So the most important tool that you have to look at your outcomes is going to be a microscope. Again, there are exceptions to this. If you're trying to work with rapidic cubic phase, we have an opaque substance. It can be really difficult to see what's going on in your drop. But for standard experiments where you're setting up sitting drop, hanging drop experiments, the microscope is the biggest tool that you have. It's the frontline defense to try to identify hits. Okay? And the microscope has a lot of sort of flexibility. Some people will just take the plate, put it on a microscope, and zip through it, and if they don't see crystals, they're done. But you really want to take your microscope and sort of look closely, increase and decrease the magnification, change the focal plane so you're looking at the top or the bottom of the plate. You can see some very different things sometimes happening. Adjust the lighting so that you can catch edges of microcrystalline material, use cross-polarization to identify crystalline material, or UV imaging to help identify something as protein instead of a salt that's forming. So imaging your drops is nice compared to a microscope because it lets you look back at your plates at your leisure, right? So if you're looking through a microscope, you're looking at the plate at one time point, say it's 1 week after you set it up. A lot of things can happen between when you first set it up and the 1 week mark. Crystals can form and then go back into solution if the temperature changes in the building rapidly, or there's a protease present that's sort of chewing things up, and a lot of strange things can happen that can make crystals that were once there disappear. So imaging your drops is a really important tool, and doing it at a regular basis so that you actually have these sort of time-locked outcomes of your experiments that you can go back to see when things start to happen. And you can also use many different tools to help characterize whether you have protein crystals or salt crystals forming in your drop. And I'm going to talk about those in detail later on. And again, if you have access to a sonic, it's great because you can use that to actually see these small crystals that you might otherwise miss. When you're looking through your crystallization experiments, you're not typically going to see some big giant crystal showing up. What you're going to see is something that looks like this. I mean, something where you might catch the glistening edges of something at high magnification under a microscope. So screening outcomes, because the sampling is so broad, you tend to hit the bare edges most of the time of the optimum conditions for growing larger crystals. So the outcome that's producing these very small crystals that you have to kind of pay attention to and really zoom in on to see, that's more likely what you're going to see when you set up a screening experiment, as opposed to something like this where you have this giant crystal popping out, which is very difficult to miss. So again, you need a lot of sort of optical illusions when you're looking at drops. So a lot of debris and things that can be present. So if you zoom in and you really pay careful attention to what's going on, you change the lighting, and sometimes you can see what's happening in the drop much better than you can if you're just looking at an initial image and you think that this little speck of dust is a crystal because you're desperate to see a crystal and you sort of will yourself to see it. So if you do will yourself to see something that may or may not be a crystal, it's important first to look back at the original image to see maybe if that something that was in the drop was present with just the cocktail before the protein was even added to the drop. And if you do still stay convinced that it's a protein crystal, then trying to characterize it first by non-destructive techniques and, if necessary, by destructive techniques to verify that it actually is a protein crystal and not just some speck of something that you're trying to fool yourself into believing is a crystal. This is just an example of a speck that somebody brought to my attention once that was not a protein crystal. So you have to be observant. You don't want to miss things, but you don't want to make something out of nothing either. Okay, I said I was going to talk about some of these different outcomes that you could have. So skin formation is a really common outcome. It's a very tough elastic layer, and Ed talked about it a little bit earlier. Basically what happens is you've got the surface of the drop, and whether that surface of the drop is exposed to air or it's exposed to a layer of oil, whatever the crystallization technique is, that surface layer has very different properties than the solution within the drop. And what can happen is the protein can actually unfold and denature and expose itself on that surface interface. When that happens, other protein molecules can come along, they can attach to it, they get unfolded, and you form this very tough sort of elastomer on the surface of the drop. It can be like a spider web to try to tease away from your crystals. It can be very tough, like literally like saran wrap, where you have to sort of pick it away with acupuncture needles or something to get your crystals out. It does not preclude crystal formation, so you can have crystal forming in the presence of the skin. Actually, quite often that can happen. And in cases like this, the skin can take on these sort of masks where it sort of fools you into thinking that you're seeing these nice long crystals. But then when you go to mount them, you realize that it's just wrinkles in the surface of the drop in the skin. Again, they form in any kind of experiment that you can set up, except perhaps dialysis. I don't think I've seen them ever from dialysis experiments. Phase separation. So phase separation is basically an oil and vinegar effect, where you've got a very highly concentrated protein phase, and it's surrounded by another protein phase that's at lower concentration. So all of the protein is never going to be contained in the highly concentrated protein phase. There's always going to be a small amount that's in equilibrium with that in the background. You can characterize this using UV light. So the protein phase will actually sort of light up with UV. As I said, UV doesn't tell you anything about the crystallinity of what you're viewing. But then you can get these sort of channels of phase-separated liquid. You can also get droplets of phase-separated liquid. And when you get the droplets, it's a good idea to really zoom in and look close at the surface of the drops, because when protein crystals form, they will tend to form on the surface of that droplet and then grow out into the less concentrated solution. Okay. So that's a known effect. So, okay, precipitates. So there are a couple of different classes of precipitates. There are good precipitates. This is a good precipitate. It's patterned. You've got these clumps and clusters of things. And then you've got bad precipitates. This wasn't Photoshop. This was actually a bad precipitate that formed, an amorphous precipitate. An amorphous precipitate forms when the protein is very highly supersaturated and just comes out of a solution, random orientations, and just forms a sort of flocculent material. So you can characterize these bad precipitates. They tend to be amorphous, cloud-like. They're often brownish in color. Proteins actually denatured in some cases. A lot of times they're associated with a skin forming on the surface of the drop, but again, skins form on the surface of a drop that contains crystals as well, so it's not by any means 100%. If you add a small amount of water to the drop, these bad precipitates tend not to go back into solution because they are denatured protein. They don't refold and go back into solution. If you add a little bit of dye, like methylene blue, to the drop, this disordered bad precipitate, it won't tend to take up the dye. If you streak through the drop and try to pick up some of that precipitate and inoculate another drop with it, you won't be able to use it as seeds. It won't produce larger crystals or other crystals from similar chemical solutions. It won't have a positive signal with the sonic, with the second harmonic generation, if you happen to have that available to you. Again, this is another example of a bad precipitate. There's basically no pattern, no modeling effect here. This is just showing that you can actually have these bad precipitates, but then have protein crystals that form in the bad precipitates. And if you think back to the phase diagram that Ed was talking about, what can happen is you can be very highly supersaturated. So the protein crashes out of solution, and it takes you from this precipitation zone. It drops the protein concentration down, where you can actually fall into this metastable zone, where you can have a nucleation event and crystals can form and grow. So it's not incredibly uncommon to actually see these bad precipitates first, but then see crystal formation take place later in time. And this is just showing that the crystals took up this chromatrope 2D dye that was used. So they were protein. Okay, good precipitates. These are the ones we want to see. They're patterned. Okay, it's not a smooth surface of stuff. You've actually got these sort of dark spots. This particular one has had methylene blue dye added to it, and you can see that these microcrystalline precipitates, they will take up dye because they're made up of these small protein crystals that have solvent channels that can actually hold the dye. Okay? A lot of these will show soft birefringence if you look at them under cross polarizers, so they'll glow very faintly. Again, that's a difficult thing to see because you get reflections sometimes, and it can fool you into thinking you're seeing something that you're not. If you add a small amount of water to these good precipitates, they'll often go back into solution because the protein is properly folded. It's in these ordered aggregates, and you can get them to go back into solution if you add water, unlike with the sort of bad precipitates. If you streak through these and grab some of these, this precipitate and inoculate other drops with it, oftentimes it will act as seeds, and you get crystals growing from those seeds. If they're chiral crystals, then you actually get a signal from SHG from the sonic if you have one available. And they often give a positive UV signal as well because they're very concentrated protein compared to the amorphous or flocculent precipitates. Okay, so again, there's a nice pattern to this precipitate. You can see that it's not a uniform distribution. This is just if you adjust the light on a standard microscope so that it reflects, you can catch edges on these microcrystalline materials that will show up, right? So you can actually see it looks like sand, it reflects the light. It helps you to identify it. In this case, it's kind of cheating, but you can actually see the small crystals in the corner. But the rest of it's, again, to go against the, to go with the, there's always an exception rule. This is fairly evenly distributed, but you can see it sort of catches the light, the edges of these small crystals. And again, it takes up the dye, which is a very easy way to distinguish it. And these are just some examples of good precipitates that were identified using the sonic. The sonic is nice because the SHG can actually act as a training tool. So there are people that spend many years in the lab, and they've been looking at drops like this under a microscope, and they can look at this image or look at this drop under a microscope, and they can tell you that's a good precipitate because I can see some coloration on the edges of it. I can detect something that most normal people can't detect. Okay? It's like reading tea leaves. They develop an amazing ability to be able to identify these microcrystals. My vision's gotten a lot worse over the years. I can't identify things as easily as I used to. The SHG, it's a pretty easy to identify signal, right? It shows up, you know that this stuff is microcrystalline, and it also helps to train you because now if you see something that looks like this, then instead of just disregarding it, you're going to maybe either want to try to get an SHG signal from it, or at least pay closer attention to it, add a dye to it, see if it really is microcrystalline material. So again, the sonic, I think, is very valuable as sort of a training tool to teach us how to recognize these good precipitates. Again, these are just a few quick examples of some of these precipitates that turned out to be good precipitates. Again, there's kind of a pattern to it. It's not an even homogeneous distribution, and some clumping and clustering here. Another example. So, okay, so examples of crystals. Okay, crystals can nucleate from a single point, and you get these sort of spherulites, these sea urchins that form. And so it's very rapid growth along one axis. Crystals like this can be optimized, right? They're perfectly viable. They aren't any good for diffraction for the most part, but it's a starting point. This is another example of a single point nucleation. So the nucleation event is taking place in the sort of center of these things, and then the crystals are growing out rapidly from that center point. Now, sometimes what you see are liquid drops. They look like spheres almost when you first look into the experiment drop. But if you look very closely, they look like little red blood vessels, little red blood cells. There's actually a little dip or divot you detect in the center of all of these things. Okay, those are not oil drops. They're actually spherulites. They're very tightly packed needle crystals nucleating from that single point. So if you can see something that looks like a red blood cell, it's something that might be worth crushing up using as a seed or trying to sort of explore further around those conditions because they can be very viable. Again, crystals don't always look beautiful. You can have these thin, twin sort of aggregated plates forming. Rapid growth. So sometimes you'll see crystals that will have these hollows in them. And those hollows are actually forming because you've basically got protein that's being delivered to the surface of the crystal, and there's this convective flow that develops within the crystallization drop when things are growing very quickly. So protein is getting delivered to the crystal through these convective flows. But what can happen is if the flow is delivering solution to the outside of the crystal fast enough, what can happen is the stuff that's sort of more interior to the crystal is only getting protein that's sort of delivered by a diffusive process. So this part of the crystal is growing a lot slower than the outside. So you can end up with these sort of bow tie looking crystals or these sort of hollowed out sections of your crystals. Sometimes you can get multiple crystal morphologies showing up in the same drop. So eventually, over time, thermodynamics is going to win this battle, and you're going to have one crystal form. But there can be periods of time where you've actually got two different crystal morphologies that sort of coexist again, it is a transient event. It's not going to last forever. And it's unfortunate sometimes when you need one crystal form and the other form sort of shows up, but then dominates, and then eventually you can't produce the form that you needed, but diffracted, and you end up with the second form and have a hard time reproducing things. Metalloproteins, which are, I think, roughly 20% or so of the proteins in the PEV right now, they can have colors. So these are faint yellow crystals, blue crystals, red crystals. Dye wasn't added to these, just the color of the crystals, because there happens to be a chromophore present. So color of a protein can kind of be a nice way to distinguish your protein crystals from salt crystals. Just a lousy example of a twin crystal, and I had to show at least one 10-egg-weight lysozyme crystal because everybody has at least one of those. And this was a slide that Ed showed earlier, but it basically just breaks down. This was taken from a set of 96 different proteins that were screened against 1,536 soluble conditions. So roughly 40% of those proteins gave one or more crystals. These were reviewed by, I'd say at least 3 people confirmed that these were protein crystals out of a set of people that were staggered, and I won't get into that, but they're sort of the gold standard of visual classification of outcomes. So about 75,000 images that we had out of 150,000 that were experimental images that were set up that were actually used and classified as the gold standards. And we came up with this distribution of the most common outcomes, right? And it turned out it was pretty interesting because from all these proteins that were set up, we found that about half of them, or 40% of them, produced clear drops, and another 40% produced precipitated drops. So only about 20% produced some other outcome that fell in between that was actually going to be interesting from the point of view of crystallization. We had phase separations were actually crystalline outcomes. Crystals are a really rare outcome. So this is a log scale, but most of the stuff you see, again, it's either going to be clear or it's going to be a precipitate. But the crystals themselves account for like 0.01% of the experiments that you're going to set up. So it's a rare occurrence. Nice looking crystals here, but we don't know for sure if they're protein, right? So these are crystals that I grew a long time ago of magnesium monohydrogen phosphate that turned out not to be the protein I was hoping they were. So the only way to tell how well a crystal is going to diffract X-rays is to actually put it in front of the beam. You can't tell by looking at it. An ugly crystal can diffract X-rays beautifully. I'm just going to quickly go through some ways that you can use if you don't have X-rays available to distinguish inorganic salt crystals from protein crystals. And I'm going to go through these, so I'm not going to read them there. First, if you're setting up vapor diffusion experiments and you see these beautiful crystals in your drop, check your reservoir, because if you see the same crystals growing in the reservoir, you have reason not to be excited about what you saw in the drop. It's a salt crystal. Okay. Dehydration, if you take your crystal out of this solution and you just leave it sitting exposed to air under a microscope, you're going to see that it very rapidly loses water and starts to crack and crumble right in front of your eyes, so you can identify it as a protein crystal. Mechanical stress, if you poke at a crystal, sometimes incredibly gently, it will just crumble apart like a piece of Parmesan cheese or very soft cake. So they're very easy to physically damage. If it's a salt crystal, you can actually hear a click sometimes when you press on it, and it'll cleave along a plane. Protein crystals typically have sort of weak birefringence. So a protein crystal on the left here, you can see it's sort of a softer, fainter signal from the birefringence than you get from the salt crystals, which tend to be very bright, glow very intensely. In the solvent channels, you can add a dye, and it'll get taken up by your protein crystals. Sometimes, it's not all the time, but it's one way that you can sort of use to help distinguish protein from inorganic salt crystals. Another thing you can do is replicate the experiment without protein. So you set up your protein buffer, it has everything except the protein in it, with the crystallizing agent that you use your cocktail. You combine them, and you just see if crystals form. If you set up that experiment with your protein and you get crystals, you set it up with the same experiment but it doesn't contain protein, and you get crystals it probably means you're forming salt crystals in your initial experiment, especially if the morphology matches. If you don't see crystals forming in the absence of the protein, then that's probably a good sign. But that said, there have been many cases that I've seen where the protein actually is required to crystallize the salt. So protein's holding on to water too. It's got other things with it, and sometimes you'll actually get the salt crystals to form only when you have the protein present, which is kind of mind-blowing. The other thing people have done, you can take wash your crystals. You want to make sure you get rid of any protein that's in the solution. You centrifuge it down. You do several washes, and then do an SCS page gel to verify that you actually have a band showing up where your protein should be from the dissolved crystals. And UV imaging, it's kind of nice because it's non-invasive. It's not 100%. There are different chemicals that can interfere with the UV signal. If you don't have tryptophan residues, you're going to not get a signal. So it's a very good technique, but 80%. I won't get into this, but just to summarize, if you set up your experiments and you review them blindfolded, it would seem like a really ridiculous thing to do. But if you can't see what's going on in your experiments, that's essentially what you're doing. Your experimental outcomes are only as good as your vision and your ability to detect crystals. So if you're looking through a very old microscope that's got 30 objectives, you're going to miss things that could be very important, hits that you could use to move on with your structure determination. So the experiment is only as good as what you can see from the experiment. Right? If you think you've identified protein crystals, you want to verify that they're protein crystals with diffraction if possible, because that's what really matters. Like I said, ugly crystals can diffract X-rays beautifully, but beautiful crystals may not diffract X-rays at all. It all has to do with the short range and long range order of the crystal. If you can't verify what you're seeing is a protein crystal and you don't have access to diffraction, use the non-destructive methods first to figure out if it's a protein crystal, and then move on to destructive ones if you have to. If you can't, and this is a little off topic, but if you get a protein crystal and you just absolutely cannot get it to diffract very well, don't keep beating the same crystallization cocktail over the head. If you have an alternate form, different chemical conditions that give crystals, don't be afraid to move on to that. I've literally seen somebody spend 2 years trying to optimize a hit, and then when they shift it over to a different chemical cocktail, they got crystals like that, where they optimize and get diffraction. So don't be afraid to modify the protein. That's the third sort of rule here. So if you don't get crystal hits and you can't really see anything that's worth moving forward with optimization, go back to the protein, reformulate it, try it, increasing the solubility, characterize it with static light scattering, dynamic light scattering. Make sure the protein's stable, which is the way you're storing it for long, reasonable periods of time. Protein's the biggest variable you have, and if you're not getting hits after you set up a reasonable number of experiments, and as close as you look and using every detection method you have available, you can't identify anything that's crystalline, then go back to the protein. That's your key variable. Okay, thanks for your attention.